Say well done, Year 11s. You've done so much work and preparation for your exams. Now you've almost finished the first set of exams, your first half. So in this session, we're just going to be covering all of the topics for GCSE Physics. I know you have it tomorrow. I hope GCSE English Literature went well today. And for those of you doing computer science as well tomorrow, good luck. But let's get started because this is a lot of content. Okay, so the first thing we need to do is do energy as a first topic. Now feel free to, whilst I'm doing this, or blurt as much information as you can, because blurting is a really good way to revise. If you have any questions or if the stream is not working, please just tell me on the chat because that'll be quite helpful. Okay. Okay. Hello to everyone who's joined. So we're going to just be revising energy now. So there's a couple of key principles that you need to know about energy that they could ask you in the exam. So firstly, the conservation of energy, which is that energy cannot be created or destroyed. Energy can just be transferred. So key thing here, energy can only be transferred. It's not made and it's not destroyed. Now there's 8 different energy stores that you need to know. You don't need to be able to, you don't need to have to list them, but you just need to be aware of the 8 different energy stores. So the first one, or what we're looking at, is thermal. Then there's kinetic. So whilst I'm doing this, feel free to blurt out all of the energy stores you know. So thermal, kinetic, gravitational potential, elastic potential, chemical, magnetic, electrostatic, and nuclear. So they are the 8 different types of energy sources. Now just going over them. So thermal energy is energy stored in heat. Kinetic energy is energy stored in movement. Gravitational potential is energy stored in its position in comparison to the gravity. So anything that's experiencing a gravitational field, so within a gravitational field, for example, you sitting here on Earth, you are in the gravitational field of Earth, therefore you have gravitational potential energy. Now, the next one is elastic. So elastic is the fact that objects can either be elastic, so when they're stretched, if they return to their original shape, that means that an object is elastic. Chemical is just in energy, so like food and petrol. Magnetic is for magnetism. Electrostatic is the particles energy, and nuclear is the energy created by nuclear reactions such as nuclear fusion. Now there's 2 ways that energy can be transferred. So just think, can you name those 2 ways? So the first way is mechanically. And the second way is electrically. So mechanical energy transfers is all about doing work. So putting a force on something. For example, if you were to push a box, you would therefore applying mechanical, you're transferring energy mechanically because you're pushing a box. However, if you were doing something electrically, the work is done by moving charges. So electrically is moving charges, mechanically is forces. And when we're looking at electrically charges, that just means things like giving out heat or giving out radiation, for example, light or sound. Okay. Feel free to ask any questions if you have any as well. Okay, the next thing you need to know is what is a system? What is a system classified of? So what a system is just an object or a group of objects that you're referring to. So say if you were asked a question, again about the pushing a box thing. So a person is pushing a box. Now the system here, imagine if it's Earth. So clearly the system is first the box, then the person, and the air around it. So all 3 of those components will make up the system. But say if the person was on space, for example, then there's no air. So that's when we call it a vacuum. and therefore it will just be a two-object system. Now, when a system changes, that just means energy is transferred. So energy is transferred when a system changes. It can be transferred into the system or out of the system. Now, you also need to know about closed systems. So, what is the difference between a general system and a closed system? A closed system is when there is no energy or matter that is being transferred. So, energy or matter, which is just mass basically, or leave the system. Therefore, the net change in energy is zero. So let's just break that down because that might be a little bit confusing. So what does it mean by the net change in energy is zero? So when you're talking about a closed system, for example, let's keep going with that box idea. So say this is a closed system. It's just the person, it's just the box, and there's no air. So this can be referred to as a closed system. Now, no energy can enter this closed system, and no energy can leave this closed system, which therefore means that the energy in this stays the same. And that's another way of saying the net energy is zero. The net energy change is zero. Okay, I hope that makes sense. Now let's move on to how energy can be transferred via heating. So energy can be transferred. Let's look at an example of a kettle. Excuse my drawing of a kettle. Okay, so that's my drawing of the kettle. Now imagine you're boiling water. So there's water in the kettle. So firstly, you're applying heat to the kettle. Therefore, you're transferring energy to the thermometer. So, but obviously, it doesn't immediately transfer to the store. So what you have is a heat element. So what happens is thermal energy is transferred from wherever the heat is coming from to the heating element and then to the water. So thermal energy transfer from the heat to the heating element to the water. This then causes, because it's going into the water's thermal energy store, it then causes the temperature of the water to rise. Now you can also think of the kettle's heating element and the water together as a two-object system, because energy is transferred electrically to the thermal energy store of the element, and it's transferred energy by heating to the water's thermal energy store. Okay. So just going over that again, this is how energy can be transferred by heating. So when energy is transferred by heating, it's normally through electrical, because you normally have to heat something with like an electric stove or something. So you have your electric stove. Your electric stove applies heat to the kettle. This then increases the thermal energy store of the heating element, which then increases the thermal energy store of the water, which then causes the temperature of the water to rise. So energy is being transferred electrically in the first stage from the stove to the heating element, and then it's just being transferred by heating to the water store. Okay. Now, energy can be transferred by heating, as we've seen, or energy can be also transferred via doing work. So what is work? Work is literally the same thing as saying energy transferred. It's literally exactly the same thing. So work can be done when current flows or when a force is moving an object. So just how we looked at the two ways in which energy is transferred. Firstly, it's transferred mechanically through a force, and the second way energy is transferred is electrically through charge. So the same applies to work. Work is done mechanically when a force is applied, and work is also done electrically when a current is applied. Now, I'm sure you don't need too many examples of work done and energy being transferred, but let's just look at an example. So imagine a ball is being dropped onto the floor. Now, a ball dropped from a height is accelerated by gravity. The gravitational force, therefore, does the work. It causes the energy to be transferred from the ball's gravitational potential energy to its kinetic. So just to simplify that explanation, if you have a ball in the air and you drop it, when you're holding it in the air, it's got its maximum gravitational potential energy. But as it starts moving, remember the energy stored in movement is called kinetic energy, and therefore you're increasing the kinetic store. But remember, energy can be transferred. So if the gravitational is going into kinetic, this means the gravitational is reducing. This keeps happening until it hits the ground, and then the opposite happens. The kinetic energy decreases as the gravitational potential energy increases. Okay, so that is the first page of energy stores and systems. Now, you are going to be given all of the equations in your physics exams. There's no point spending too long revising them for the 2023 exams. So you just need to know kinetic energy, energy stored in movement. So anything that is moving has energy in its kinetic energy store. Energy is transferred to this store when an object speeds up, and is transferred away when an object slows down. Therefore, that means that if you're having an accelerating object, this means that the kinetic energy stored is increasing, and vice versa. So the equation for kinetic energy is half times mass times speed or velocity squared. This then means that kinetic energy is reliant on both mass and speed. So lifting an object raises gravitational potential energy. So you've got kinetic energy here, gravitational potential energy. So gravitational potential energy, as we said, is energy stored in its position, in an object's position. Therefore, if you have an object that's on a table and an object that's on the floor, so let's do object on table, an object on the floor. The object on the table has a higher gravitational potential energy because it is higher. So if you look at the equation of gravitational potential energy, it is mass times gravitational field strength times by height. So imagine if the mass of the boxes were the same, then if this table height is 2 meters and the ground is obviously, say, 0 meters, then you can tell that the height for this one is going to just be 2 meters more. But here it's just nothing. So as you lift an object, the gravitational potential energy store of that object increases. The amount of energy in this gravitational potential energy store depends on the mass and the height. Okay, so falling objects also transfer energy. So when something falls, energy from its gravitational potential energy store is transferred to its kinetic store. So the opposite happens here. So when something is being lifted up, the gravitational potential energy store increases. But if something is fall down, the gravitational potential energy decreases and kinetic energy store increases. Therefore, the energy lost from the gravitational potential energy is the same as the energy gained in the kinetic energy store. Now, stretching is all about elastic potential energy. So you should know what an elastic object is. An elastic object is an object that when stretched, and when the force is removed, it returns to its original shape. So, elastic potential energy returns to its original shape. Therefore, when we're looking at an elastic potential energy graph, as long as it doesn't exceed its limit of proportionality, which would be here, which means as long as the string isn't stretched too much, or the spring isn't stretched too much, then the extension will always be constant to the energy inputted. Okay. Now moving on to specific heat capacity. So just an overall revision of everything we've covered so far. So we've looked at the different types of energy transfers. How energy can be transferred via two ways, mechanically and electrically. So mechanically is via forces, electrically is via charges. We looked at what a system is, and we learned that a system is just a fancy word for a single object or a group of objects. Now, when a system changes, that means that energy is transferred, and it can be transferred into the system or away from the system. But if it's a closed system, that means no energy can be transferred in and no matter can be transferred out. So therefore, the net change in energy is zero. We looked at how when you're heating a kettle, this supplies thermal energy to the heating element electrically, and the heating element heats up the water mechanically. And then we looked at the two types of work, what work means. It's just energy transferred, again, mechanically or electrically. And then we talked about the different types of energy. So kinetic, which is the energy in motion. So if there's an accelerating object, that means that the kinetic energy stored is increasing. You also have gravitational potential energy, which is the energy stored in its position. So you can see that a box on a table has double the gravitational potential energy as a box just on the floor. It's all about the height. And therefore, when you're lifting an object, you're increasing the gravitational potential energy. And when you're dropping an object, you're decreasing it. We looked at elastic potential energy, which is for elastic objects that return to its original shape after the force has been removed. And we looked at the limits of proportionality. So that's a lot about energy. We're now going to be looking at specific heat capacity. So specific heat capacity. Now there is a required practical for specific heat capacity that you're going to have to know. So specific heat capacity is really how hard it is for an object to heat up. So the actual definition, the physical definition that you need to know is specific heat capacity is the amount of energy needed to raise the temperature of an object by 1 degree Celsius. And this object has to be 1 kilograms in mass without changing the state. And we'll look at why it's important to say without changing the state really soon. But let's just focus on the equations now. So you will be given the specific heat capacity equation in the exam for 2023. And it's going to be written as change in energy is equal to mass times by the specific heat capacity times by the change in temperature. But the question, if you do get a calculating question, will ask you to find the specific heat capacity, which means you will either have to rearrange the equation or just work it out from here. So if you were to rearrange the equation, then you can just draw a triangle. So change in energy is equal to mass times specific heat capacity times temperature. And if you wanted to find the specific heat capacity, you would therefore do the change in energy over the mass and the temperature. Okay. So specific heat capacity, basically how hard it is or how difficult it is to heat up an object. That's pretty much what it means. So what happens is more energy needs to be transferred to the thermal than others. So say if we had two given materials, material 1 and material 2. Material 1 may take 4,000 joules of energy to increase the temperature by 1 degree, whereas material 2 might just take 400 joules of energy to increase it by 1 degree Celsius. So that's what we're looking at. We're looking at specific heat capacity. And let's look at an actual example. So that's material 1 and material 2. In terms of real life examples, you can use the examples of mercury and the example of water. So water, the specific heat capacity of water is 4,200 joules needed per kilogram. Whereas the specific heat capacity for mercury, to increase it by 1 degree Celsius, is 139. The greater the specific heat capacity, the more energy required to heat up an object. So therefore, water takes longer and is more difficult to heat up than something like mercury. So materials that need to gain lots of energy in their thermal energy stores to warm up also takes a lot of energy to cool down. So if you were to heat mercury, for example, then it would really quickly become increase in temperature, but then because of the low specific heat capacity, it will always also be really quick to reduce back to that original temperature. Whereas with water, if you spent a longer time heating it up, then it would also take a longer time to cool back down. Now let's look at the specific heat capacity required practical. So this is the first required practical for physics. So what you're going to do is your aim is to try and measure the specific heat capacity of certain materials. So what you're going to do is firstly you're going to have this aluminium block. So let's draw this out. Now the aluminium block is going to look like this. Let me colour it in so it's easy to see. Now this actually can be aluminium, it can be copper. Doesn't matter too much. Now this aluminium is made in a special shape so that it amounts to exactly 1 kilogram. So you've got 1 kilogram of aluminium here. So you're ready with the mass. Now you have 2 holes you can see. So in the first hole, you're going to put the immersion heater, which is basically the thing that heats up the metal block. So let's just write that, immersion. The reason why it's called the immersion heater is because it needs to be fully immersed in the aluminium block. Because if there is a gap between the immersion heater and the aluminium block, that means that temperature can easily be wasted. So that is a key principle there. So you've got the immersion heater, the aluminium block. What goes in the other hole? The other hole goes the thermometer. So the thermometer is the device that you're going to use to measure the temperature change. So you've got the immersion heater heating up the aluminium block. You've got the thermometer measuring the temperature change. Now, obviously, the immersion heater, the energy is transferred electrically, so it has to come from somewhere. So let's just draw a diagram for where we get it from. So the immersion heater is connected in series to an ammeter. Remember, ammeters are always connected in series to circuits. And then you also have the power supply. And then you have it just connected back to the immersion heater. Now, if you don't know the current of if you don't know the power supply, then you can add a voltmeter to find that. Is this on times 2 speed? No, it's not. I don't think so. Okay, I'll slow down a bit then. Thank you for that. Okay. Well, maybe it's just the issues with the live stream. Let me just check that 1 second. Hi everyone. Just tell me if it's working or not, if the chat is if the audio, sorry, is okay, because I could see there was a bit of issues with it before. So yeah, just tell me if the audio is coming out of it. Okay, thank you for that. Just feel free to tell me whenever it like starts messing up. I'll fix it again. Okay, so going back to this, so this is a required practical for specific heat capacity. So what you have is firstly the aluminium block. So that's that black thing you can see here. This is 1 kilogram of aluminium. It could also be copper. It doesn't really matter what metal it is. You just need to know that it's definitely got to be 1 kilogram. Then you have these two holes in this 1 kilogram. And in the first hole, you have what's called an immersion heater. So the immersion heater will be the device used that will heat up the aluminium block. And in the second hole, you're going to have a thermometer. The thermometer will be used to measure the temperature change. Now, a key tip here, which they tend to ask in your exam, and that could give you extra marks, is why they would sometimes put water at the bottom of the thermometer. Now, try and answer that yourself if you can. Why do you think they put water at the bottom of the thermometer? I'll give you a few seconds. Okay, so the reason why they put water at the bottom of a thermometer is to increase the thermal contact. Now, what that means is sometimes the thermometer, the bottom of the thermometer, will not reach the bottom of the aluminium block, and therefore the temperature that it's measuring is not as accurate as it can be. So, if using a pipette, what it will do is it will increase the accuracy of the temperature reading that the thermometer is giving you. Okay, so that's what thermal contact is, the use of water. Now, then the immersion heater is connected to obviously a power supply, which also has an ammeter. They're all connected in series. Now, another thing that you can do that, if you're asked about this in your exam, will give you extra marks, is if you say wrap it in insulation. So imagine this green thing is insulation. Now, I believe you can kind of guess why you would want to wrap it in insulation, because obviously you want to reduce heat loss as much as possible so that your reading for the specific heat capacity can also be as accurate as possible. Okay, so insulation can be used. This can be newspaper, this can be cardboard. Now, firstly, what you want to do is you're going to measure the initial temperature of the aluminium block. Then you're going to set the potential difference of the power supply to 10 volts. You turn on the power supply and you start a stopwatch. So what you're doing is you're going to set the power supply to 10 volts. You're going to start the stopwatch and you're going to record the different temperature readings. So say at 30 seconds, the temperature reading, at 60 seconds, the temperature reading, probably more frequent than that, probably like every 15 seconds would be much better. So then you would record it in a table. So 10 volts, you can increase the voltage, 20 volts, 30 volts, 90 seconds. So what you'll do is you'll record the temperature value after 30 seconds in here, you'll record the temperature value after 60 seconds for 10 volts in here, etc., etc. Now, when you turn on the power, what will happen is the current in the circuit does work on the heater. So the current travels around the circuit when you turn the power on, like this, goes around, does work on the heater, and therefore energy is transferred electrically to the heater. And this energy is then transferred to the aluminium block, and then it goes back around the circuit. Oh, sorry, there's a bit of issues. 1 second. I hope that makes sense. If you have any questions about this required practical, do continue to ask. So remember, that's not the end of the required practical as well. You also need to calculate the actual specific heat capacity, because that's the whole reason why it's called that. Your job is to calculate it. So you're going to be given the equation as usual, specific heat capacity equation. But how do we calculate it from the values we've got? Because we know that specific heat capacity is the change in energy over mass times by the change in temperature. But how do we measure the change in energy? That's probably the hardest thing. So in order to measure the change in energy, you're going to need to know this equation. So you know that when you've collected enough readings, you're going to use your measurement of the current, your measurement of the potential difference, and find the power. So power, in order to find the change in energy, you're first going to find the power. Power is just the current multiplied by the voltage. So you're going to have as you're recording the temperature values in each of these boxes, you're also going to be recording the current value. So you'll be doing the current to multiply by the voltage to get power. And if you know the equation, power is equal to energy transferred over time. Now that's the purpose of the stopwatch. So as you've calculated power and you want to find energy transferred, you will therefore do power multiplied by time. So you will therefore do the result of this calculation multiplied by the different seconds. Okay, I don't know if I explained that very well. Okay. Okay, do tell me in this chat if you understand this practical. Do I need to go over it again? I don't think I explained it to the best. But okay, so once you've found the energy transferred, you're going to draw a graph. And on the x-axis, you're going to have the energy transferred. And then on the y-axis, you're going to have the temperature. Now, obviously, as the energy transferred increases, the temperature increases. So the graph should look something like that. Now, the reason why it's flat in the beginning is because at first it takes a little bit of time for the entire block to heat up. But beyond that point, then the change is constant. Okay. I hope that makes sense. So just a reiteration of the required practical. So you've got the aluminium block, 1 kilograms. You know the mass. You've got the immersion heater. You've got the thermometer. The immersion heater is connected to a power supply, and the power supply will tell you the voltage. The ammeter will tell you the current value, and then you're going to have a stopwatch as well. Now, after every couple of seconds, so say every 15 seconds, what you're going to do is you're going to record the current value, you're going to record the voltage, and you're going to record the temperature. And then what you're going to do is, in order to find energy transferred, you're first going to do power is equal to current times voltage. And then the reason why we're finding power is because we know that energy transferred is equal to power multiplied by time. So once you get that result of I times V, you're then going to times that by the time, and you'll get your energy transferred. And then once you've done that, you're then going to plot it on a graph, energy transferred on the x-axis, temperature on the y-axis. The graph should look like this. The purpose of this being flat initially highlights how it takes a little bit of a while initially for the aluminium block to heat up. But eventually, beyond that point, it then gets constant, the temperature. That's the first required practical. I hope that makes sense. You can then work out the specific heat capacity by just doing 1 divided by the gradient of this line. And you can do this for different materials. So if you wanted to measure the specific heat capacity of different materials, instead of aluminium, you could do copper or loads of different metals. Okay, so required practical 1 done. Let's move back on to content. So the conservation of energy principle is quite clear. You probably would have learned this in year 7. Energy can be transferred, but energy cannot be created or destroyed. Now, when energy is transferred between stores, not all of the energy is transferred usefully into the store. Some energy is dissipated. Dissipated energy is called wasted energy. So dissipated energy just refers to the amount of energy that's just wasted in the surrounding, and therefore that's why it's called wasted energy. Now let's look at some examples. So have you ever been on your mobile phone? You probably have, and it's after you've used it for quite a while, it starts to get a little bit hot. Now, the reason why it starts to get a little bit hot is because currently in your phone, you have your battery. And what type of energy is stored in a battery? Hopefully, you said chemical energy. So you have your chemical energy in your battery. Now, some of this energy is usefully transferred electrically to make your screen, but some is also wasted. And what is it wasted as? It's wasted as thermal energy. And that's why your phone gets hot after you're using it for quite a long time, because the energy is dissipated as thermal energy. Now, that's quite a useful way to remember the conservation of energy principle because it's something you can relate to. Okay. Now let's look at power. So we already used the equation power is equal to energy transferred over time. Now, if you have anything over time, then that means that this value here is measuring the rate of something. So in this case, we have energy transferred over time. Therefore, power is basically measuring the rate of energy transfers. So if you were ever asked what is the definition of power, power is the rate of an energy transfer. Now, power is measured in something we call watts. But energy transferred is measured in joules, time is measured in seconds, so it could also be measured in joules per seconds. It's the same, it's the equivalent. So 1 watt is equal to 1 joule per second. Now, a powerful machine is not necessarily a machine that exerts a strong force, although it usually ends up that way. So a powerful machine is one that transfers a lot of energy in a quick amount of time. So that's what we call a powerful energy, a powerful thing. So for example, if you've got 2 cars and we want to see which car is more powerful, it won't necessarily be the one that exerts the strongest force. The more powerful one is the one that transfers more energy over time and therefore ends up being much more speedier. So say if they both transferred 4,000 joules of energy. However, car A transfers this in 10 seconds, whereas car B transfers in 1 second, then car B is therefore 10 times as more powerful than car A because the rate is much better. Okay, so that's enough of the conservation principles. Now on to conduction and convection. Now, I have a feeling that this may come up in the exam this year because it hasn't really come up too much recently. So it might be important to pay attention to this topic. It's often forgotten. So what is the difference between conduction and convection? Well, conduction is the process when vibrating particles transfer energy to the neighboring particles. So imagine we have a diagram here. Remember, these particles are in fixed positions, which is why they vibrate. Now imagine the energy is yellow. So conduction is a transfer of energy through vibrating particles to its neighboring particles. Important to say neighboring particles because obviously it wouldn't, if you had a metal block, for instance, and you started applying heat on this corner, on the left corner, then obviously heat will transfer from the left corner and spread out through the metal. It wouldn't make sense for it to start here and end here, and end here. Heat starts from where you start heating it and it's most hottest here and then spreads out. That's why it's really important to say conduction is where energy is transferred through vibrating particles. So vibrating will be your first mark, and the second bit will be to its neighboring particles. Okay, so that's conduction. Now, the reason why the particles start to vibrate is really important because sometimes you might be asked, how does conduction work? And you have to go into a bit more detail than we just looked at now. So when we're looking at conduction, what happens Let's look at it now. So imagine you're applying it. What happens is as you're applying the heat, there's thermal energy being supplied. Now remember, it is transferred. So energy is transferred from the thermal energy store of whatever's being heating it. So say it's Bunsen burner. So from the thermal energy store of the Bunsen burner to the thermal energy store of the metal block. That then means it's gaining energy, and because it's got more thermal energy, it also increases in its kinetic energy. And because it increases in its kinetic energy, that is the reason why the particles start to vibrate. Because remember, kinetic energy is the energy in motion. So if you're increasing the kinetic energy by increasing the thermal energy, you'll therefore vibrate and move. So energy is transferred to an object by heating. It's transferred from the thermal energy store of the heater to the thermal energy store of the object. It's then shared across the kinetic energy stores of the particles. So key thing, it's shared between the kinetic energy stores. The particles in this part of the object vibrate more because they have kinetic energy. Now, because they vibrate, this is talking about the specifics of what does a vibration mean. It just means the particles are colliding with each other more. And as they collide more, we know from physics later on that as the more collisions there are, then the more energy is transferred between the particles. And this is a process of conduction. So just summarizing that, what happens is you've got thermal energy from the source, it's transferred to the thermal energy of the object, and then the thermal energy then causes kinetic energy to be shared across the particles in that metal block. This then causes vibrations as the particles start to collide. As the particles collide, this then means that more energy is transferred and energy is transferred more quickly. Now, this process continues throughout the object until the energy is transferred to the other side of the object. It's then usually transferred to the surroundings. So, what this means is you have your heat source, you have your box. So, if you've got your heat source, then what the heat will do is it will keep moving all the way through the object and then eventually go into the surrounding air. It won't just stop at one part. Now, you also need to know what thermal conductivity means. Now, conduction is a process where vibrating particles transfer energy to neighboring particles. Then thermal conductivity is practically how quickly this energy can then be transferred. So thermal conductivity is how quickly energy can be transferred through a material via conduction. So therefore, if you're saying that a material has a high thermal conductivity, that means that the energy is transferred very quickly. So these are things like metals. Whereas if it has a low thermal conductivity, these materials tend to be insulators. They're really bad at transferring energy. Things like glass or plastic, and that's why they're used over wires. Now, that's enough of conduction. Let's look at convection. What is convection? So we looked at conduction, vibrating particles transferring energy to its neighboring particles. Convection is what happens in what we call fluids. So remember, fluids are not just liquids, they're gases as well. So you've got gases and liquids. And it's practically when you have these really energetic particles, because remember, particles are much more energetic in a liquid than they are in a solid, and particles are much more energetic in a gas than they are in a liquid. So you have your energetic particles, and because they have so much energy, this causes them to move away from a hot region to a cool region. Now, a lot of people think convection is harder to understand, but it makes more sense naturally. Because if you think about it, say if you had a heater here. Okay, so imagine if this was a heater, a really weird looking heater. So the heater is basically emitting this very hot, basically high energy particles. Now, as the heater emits these high energy particles, somehow the room gets hot. And it makes sense because naturally we think that the heat will spread out. And the reason why we spread out is what we call convection. It moving from a hot region by the heater to a cool region at the other side of the room. And that's how energy spreads out, thermal energy spreads out. Okay, so that's convection. Now, as we said, it can happen in gases and liquids. Energy is transferred of the liquid or gas. And this energy is then shared across the kinetic energy stores. So imagine you have a beaker, and this beaker it's a sealed beaker, sealed container, and you've got a gas. Now, as you heat it, what you're doing is you're transferring thermal energy to the thermal store of the particles. Now, as you're transferring it to the thermal energy stores of the particles, this then means that the energy is shared across the kinetic energy store. It's important you say that. So it goes from thermal energy, the energy is then shared across the kinetic energy, which I'm just going to write by doing KE. So shared across the kinetic energy store of the particles, and that then causes them to move more and gain more energy. So move more, collide more, and transfer the heat across more. So that's pretty much what happens. So if you're asked to describe what happens when you heat a gas, you're supplying the thermal energy. This then causes the thermal energy of the gas particles because energy is transferred, and this then means kinetic energy store of the particles. Now, if you were asked to talk about what happens when you heat a liquid, it would be a very similar thing. So you have your liquid here, still made of particles. Remember, the difference between liquids and gases is that liquids have a little bit less energy, but they can both flow, and they have a little bit more stronger forces of attraction. So if you're heating a liquid, you're supplying your thermal energy, whatever you're using to heat, to the thermal energy store of the particles, and therefore energy is shared between the particles, them to move about and eventually change state. Hi, just advice. I think you should upload these streams later as videos. Oh, okay, thank you. That's actually really good advice. I'll try and make sure I do that. Yeah, that's a good idea. I should do that. I think I'll do a computing one later this evening. That's why, because I wanted to help you guys prepare for both GCSEs tomorrow, because I know some people do computing. That's why I did this one a bit early. But yeah, that's good advice. Thank you. Okay. Now we've talked about convection. We've talked about conduction. We also need to look at radiators. So you may be asked about radiators or something that works in a similar way to a radiator. So if you have a radiator in your room, it might be quite helpful to just literally look at it and memorize this process, because then you'll assign it with an image. So you have your radiator, and what the radiator does is it generates convection currents. So the radiator is very hot. It heats up electrically. So you don't need to know the ins and outs of that. You just need to know that the radiator heats up electrically. That means that the air, imagine if there's clouds of air here. So the air in front of the radiator then gets hot because obviously the thermal energy transfers from the radiator away from the radiator to the gas. As this air gets hot, it then spreads out around the room. And eventually, this hot air then gets cool again. So it then goes back to the floors of the room. And then there's this whole cycle. So there's this cycle from the hot energy, the thermal energy of the radiator heating up the air, it then turning into a cycle and going like that. Okay. That's a very bad diagram. I'm surprised if you understood what I just meant, but hopefully you should, because all that's basically happening is a radiator is heating up the air. This air then moves across the room, and then the air comes back when it gets cool. This is called a convection current. Okay, so we're almost finished with the first topic of energy. So we just need to look at ways in which we can reduce the unwanted energy in our homes. So how do we reduce energy waste in our homes? Well, there are two main ways which we can reduce energy waste. So the first way is through lubrication. And we'll talk about that in a second. And the second way is through insulation. So if you were asked what are the two ways of reducing energy transfers, then talk about lubrication and insulation. So just a key thing about friction and why is energy wasted, first of all, because you may be asked, why is energy wasted? So the reason why energy is wasted is because of friction. Literally every time energy is wasted, friction is always the culprit here. Just think of it as the evil thing. So the reason why friction is the culprit, because imagine you have two objects moving. So let's use your hands as an example. So you do this. So as you rub your hands, normally anything that moves, there's a frictional force. So as you rub your hands, this then causes friction to act against it. Now, this causes energy in the system to then be dissipated. So as you rub your hands, you should have kinetic energy, but some of the kinetic energy that's transferred from the chemical energy store of your muscles is also wasted as thermal energy, which is when you move your hands, even though it should be kinetic energy, you also feel it getting warmer because of the thermal energy. Just someone's question, will the formula sheets have words on them or just symbols? So the formula sheets will have words on them as well. They'll have words, they'll have letters, but they won't have the units. So that's something that you need to know, the units. For the topic that we're on right now, we are on reducing unwanted energy transfers. We're almost done with the first topic, energy, and then we're moving on to electricity, if that makes sense. Maybe I should write that in the thing so everyone knows. So currently on energy. If you do have any questions, by the way, feel free to ask them. Is it Edexcel or Cambridge? This is AQA actually. So none of them, unfortunately. I don't know. Unfortunately, it's not. Okay, so just continuing on. So that's friction. Friction causes all unwanted energy transfers because anything that moves, friction is always created. There's always an opposing force, and in this case, it's friction. So for objects that are being rubbed together, that's how we can help lubrication. So lubrication, what is lubrication? Lubrication is basically reducing the friction between the object surfaces. It's usually liquid. So if you added oil, for example, when you were in the midst of rubbing your hands, what happens is the oil in your hands, and therefore because it's smooth, this means that the surface is less rough. And as the surface of your hands is less rough, this means that there's less friction and therefore it can flow quite easily and coat them. Just your question, on the formula sheet, it will say kinetic energy. Yes, it will say kinetic energy. By the way, you can access the formula sheets for your exam. If you search up 2023 Physics formula sheets. It will be there because they have to let you know what formulas that they're going to tell you. So it is online, available online, if that's helpful. Okay, so we've looked at lubrication. That's the first way. Mostly lubrication is oil, but you also need to be aware that sometimes other liquids are used as well. So it tends to be oil. Now, what about insulation? So how does insulation reduce energy loss? What it does, insulation reduces the energy transfers via heat. Basically, you get a material with really low thermal conductivity, meaning it can't really conduct much heat just because of the structure of it, and you place it around something that conducts a lot of heat and it just encloses it. Just like the reason why you're wearing clothes right now, or clothes in the winter, like a t-shirt. What happens is a t-shirt acts as a insulator, and one second. Sorry about that. Okay, so yeah, energy transfer. So when you're wearing a top, basically what happens is you're trapping the heat because of the fact that it is an insulator, and obviously that's a efficient way to reduce energy waste because energy produced by your body is therefore being trapped in the clothing. With your question, I'm writing my edX GCSE Physics tomorrow. I'm searching for revision videos. Any suggestions? I know people who do revision videos for IGCSE maths, but I'm not sure about physics. I'm sorry, I'm actually planning on doing IGCSE videos, but obviously it won't help you in time, I'm sorry. But I'm not too familiar with IGCSE. Sorry for the inconvenience. But okay, reducing energy waste. So we've talked about lubrication, we've talked about insulation. So insulation basically reduces the rate of energy transfer via heating. So there's different methods of insulation, and you might be asked, what are the different methods of insulation in and around the home? So home insulation. Now, the different types of home insulation. Firstly, you can view carpet as insulation because obviously there's floor beneath the carpet, and if there was just floor beneath the carpet, then the room will get really cold because the energy that's being transferred naturally in your room, because you're a human, so you make thermal energy, it would just go straight through the floor. However, if you had carpet, which most people will probably do, it prevents the energy going and escaping through the floor and through drafts. So carpet is an example of home insulation. Another example is thick walls. So having thick walls that are made from materials with a very low thermal conductivity. So, things like foam. Foam has a really low thermal conductivity, therefore that's used. And also, you can also have things called cavities. Now, if you've ever seen double glazing windows, or if you looked at walls, so imagine this is your room and this is the outside bricks. If there was just nothing in between, if there was just like this thin, if the wall was just that thin, then we'll be in the danger of energy being transferred straight outside and wasted. And we don't need that. So what happens is sometimes they just leave a gap in between the bricks and the room. This means that there's just air here. Now, air is a really bad, what's it called? Has low thermal conductivity. It transfers energy really badly, and therefore the energy in the room won't be able to get across to the bricks, so it will more likely just stay in the room. But sometimes people take this a step further, and instead of just putting air, they put foam, which is just sometimes called insulation. And what this foam does is it literally through, so it just repels it. The room stays nice and warm, and you don't get cold in the winter. Okay, so double glazed windows. Double glazed windows is a very similar idea to this. So imagine if you had a window. Now, double glazed window just means that it's much harder for energy to be wasted to the outside surrounding. Yeah, it's much harder for energy to be wasted to the outside surrounding because you have a really tiny gap of air, which just makes it really difficult for heat to penetrate through there. Okay, so that's all about energy transfers and how to reduce unwanted energy transfers in and around the home. Let's look at the second required practical. So we've looked at specific heat capacity. The next required practical is thermal insulation. So this is required practical number 2. Now, it's annoyingly the required practical number 1 and required practical number 2 both involve heating and water. So try not to get confused when they're asking you about it. Okay, so the aim of the first one, specific heat capacity, was so you could calculate specific heat capacity. But the aim for this one is to try and see which materials are really good at being an insulator. Okay, so what you'll have is you're going to start with a small beaker inside of a large beaker. So a small beaker inside of a large beaker. If you want to gain those extra marks, you could just say a 50 centimeter cubed beaker inside of a 100 centimeter cubed beaker. So in your mini beaker, you're going to have this little cardboard lid. Now, the reason for the cardboard lid is, to just prevent the heat escaping, because what you're going to do is in the beaker, you're going to have very hot water from the kettle. Now, in the cardboard lid, you have to poke a little bit of a hole because you're going to have the thermometer. Now, if you want to take it a couple more steps, you can also have a massive cardboard lid on the overall beaker if you wanted to. But that's just, that's a bit unnecessary. So what you're going to have is the reason why we have a small beaker inside of a large beaker is because you're going to be wrapping the small beaker with different thicknesses of material or with different materials. So either you'll be asked to evaluate the effectiveness of different materials as thermal insulators, and in that case, you need to make sure the amount of times you're wrapping it around the beaker is the same, but the different materials are the independent variable. Or if you're looking at how the number of layers affect the ability for it to be a thermal insulator, then you'll be changing the number of layers at each go. So, okay, let's talk about the actual method now. So firstly, what you want to do is measure the initial temperature of everything. So measure the initial temperature of the water. Note that the water has just been boiled from the kettle, so it's going to be quite high. Okay? And this should be the highest temperature value that you get, because obviously from that point onwards, it's going to start cooling down quickly. You're then going to try and seal the container as quickly as you can, and you're going to leave it for 5 minutes. So you're going to leave it now for 5 minutes. So therefore, in order to find out that it's 5 minutes, you're going to have to use a stopwatch. And then after 5 minutes, you're then going to record the temperature value. Now, obviously, it would have gone down from what it was previously, but in case of the different materials or the different thicknesses, then you're going to get different values for how much the temperature decreases. Now, you can you can continue this onwards. So you can use smaller intervals, 5 minutes, 2 minutes, 3 minutes, it's up to you. Now, you're going to complete this and repeat this experiment with different materials or different thicknesses. Remember, you have to pour away the water and use freshly heated water from the kettle, because obviously it wouldn't be fair to have different starting temperatures. You're trying to have as much as a similar starting temperature as possible. So once you've done this, you're then going to repeat it for the different materials or different thicknesses, and you're going to draw a group. Say if you measured the effect of the different types of insulators, what you're going to have is you're going to have all start from the same temperature. So the temperature is on the y-axis and time is on the x-axis. So they're all going to have the same starting temperature, but some will be like this, Some will be like this, some will be like this. And obviously, you can tell that, say, let's call this line. So this first line here that you can see is the best insulator because it has the least steep curve, which means that the least amount of temperature reduction over that time. And therefore, if there's the smallest temperature reduction, that means that it's a really good insulator. Whereas if you can see this line here, this line is really steep, which means the temperature decreased really quickly, which means that the insulator used can't be that good if the temperature decreased that quickly. Okay, and that's all you need to know for the required practical for thermal insulation. Now so let's look at the final couple of topics for the topic of energy. This went a lot slower than I expected because I've been putting a lot of emphasis on this. So I'm sorry, I hope I'll be able to get through the whole of physics, but I hope what you've looked at today is helpful revision for tomorrow. So let's look at efficiency now. So efficiency is just how much of the output energy that is useful compared to the total input energy. For example, you could use this in your studying. So say if you're trying to study, right? Imagine there's your books. So how much energy do you need to input to study? Say, just give this a random value, say X, for example. You need to input X information to study. But how much of that X energy was actually turned out to be useful studying? I'm pretty sure it's not 100%, right? Because of some, which is wasted energy, or what we call procrastination. So just think of energy transfers as the same thing. Imagine the total input energy is how much energy you initially want to give, and the useful output is how much actually is of use. Now, you're obviously going to be given this equation. Efficiency can also be referred to as useful power output over total power input. Now, efficiency is always out of 100. You can put it as a decimal, for example. So say if it's 0.7 or 70%, they're the same value, so decimal or percentage. Now, useful energy output is almost always never equal to the total energy input. Why? Because energy is always wasted in some way or another, except for one instance, which we call the electric. The reason why no wasted here is because the total electricity going into the heater actually all goes out as thermal energy. And normally we consider thermal energy wasted energy, but in case of a heater, thermal energy is clearly useful. And that's why electric heaters can have the potential to be 100% efficient. Okay, we now need to look at energy resources and their uses. So renewable, non-renewable, wind, hydroelectric, geothermal, biofuels, non-renewable. Topics are much shorter than the ones we've looked at, so don't worry about this one too much. So firstly, non-renewable. What are non-renewable energy resources? Now, you assume that maybe you know the definition, but sometimes we forget. So non-renewable is basically energy sources that will one day run out. Eventually, it's just going to run out. That's what a non-renewable energy source is, and therefore a renewable energy resource is the energy that will never run out. So non-renewable energy resources are things like fossil fuels, nuclear fuel. So what happens is with fossil fuels, you basically have these natural resources that form underground over millions and millions of years. And then eventually what happens is they're typically burnt to release lots of energy. Now, the reason why it will one day run out is because we're using it at very fast of a rate. And also, it takes millions of years to form, therefore, it will take ages to rejuvenate. Now, what are the three main fossil fuels? You've got oil, coal, and gas. Now, gas, sometimes they ask you to refer to it and and things like that. So, renewable energy will never run out. So, it can be renewed at the same rate it's being used, basically. Most of them do actually damage the environment. Ironically, renewables do because of things like hydroelectric power, but they are less worse ways than in comparison to non-renewable. However, another issue is that they are not very reliable, or they're definitely not as reliable as non-renewable. Okay, so how are energy resources used? So let's look at some energy resources. So the main use of energy is transport. Transport is one of the most obvious places where you have fuel that's being used. So in terms of non-renewable, I'm just going to show non-renewable by NR and renewable by R. So non-renewable examples of transport are things like petrol, things like diesel. These are all created from oil. So petrol and diesel are created from oil. How to remember that petrol and diesel are created from oil? Well, if you remember the crude oil, fractional distillation, that all comes from oil and you get petrol and diesel distilled from there. So petrol and diesel all come from oil. Coal is sometimes used in some old-fashioned like trains and things like that, but not necessarily in the modern times. Now, in terms of renewable transport, you now have things like biofuels. Don't make the mistake being electric for renewable transport because the electricity is generated mostly fossil fuels. Therefore, it doesn't count because it's not a source. So you've got your biofuels, which is basically, natural things that just get burnt. So plants, human waste, animal waste, things like that. Okay. And you've got heating. So the two main uses of energy in the world, transport and heating, or at least in the UK. So how are there non-renewable heating? Most of the heating in the UK, where we have transport, is mainly oil. Heating is mainly natural gas. It's the most widely used fuel for heating homes in the UK. Now, the gas is used to heat water, and this heated water is then pumped around our homes, making us nice and toasty. Coal is commonly burnt in fireplaces, maybe not as common now. And you also have electric heaters. So you have natural gas and you have electric heaters. Now, in terms of renewable heating, you have geothermal. Now, geothermal is just things like hot rocks or volcanoes that lie near the surface, and the energy is just used from these um, geothermal rocks to heat things. Now, you may be asking, how are these rocks just randomly hot? Well, the reason why it's randomly hot is because of, decay of radioactive elements. So things like uranium. And as they break down, they release a lot of energy. So geothermal. That's where that's from. So you've got geothermal. You also have solar powered heaters, not as common right now, but maybe they'll become more common. So just to review what we've looked at, non-renewable is energy that will one day run out. Things like the fossil fuels, which is oil, gas, and natural gas, and coal. Renewable energy will never run out. They are not as reliable and they do have a bad impact on the environment, but lesser of an impact than non-renewable. Now, the main uses of energy, you've got transport, you've got heating. So in terms of non-renewable for transport, you've got petrol and diesel, which are derived from oil. You've got coal for some ocean trains, and in terms of renewable, you've biofuels. And for heating, most of the heating is generated through natural gas and electric heaters, but you also have geothermal and solar powered for renewable resources. Okay, finally, all you need to know now is how the different energy sources are procured. So you've got wind, solar, geothermal. They're the first three. So wind is where you have these wind. They are high up in exposed places and things like normally around coasts where there's a lot of wind. And what happens is each turbine has a tiny generator inside of it. And as the rotating blades turn, this then turns the generator. So all you need to know is that wind is generally found in coastal slash exposed areas. What happens is as the blades turn, the generators that are installed inside of them then turn, and obviously as the generators turn, electricity is produced. So advantages of wind: there's no pollution, it's free, it's reliable. Some people say in terms of disadvantages, they spoil the view, they can be very noisy, and they harm birds, and also the initial costs are quite high, although there are no fuel costs and minimal running costs as well. Okay, so solar cells. Solar cells gain electric currents directly from the sunlight. Loving this. Oh, thank you. I'm glad you find it helpful. Thanks for the little encouragement. I hope you guys are not enjoying your exams, but I hope it's going fast for you so you don't have to suffer as much. Okay, so solar cells generate electric current directly from sunlight. So electric current comes from sunlight. There's not too much you need to know about solar cells. You can think of sometimes they use, I don't know if you've ever seen those calculators that are solar powered, but solar power can also be used for like greater things like the electricity in a household. So solar power has a lot of capacity. However, what is the issue with having solar power in England? Well, there's not enough sun to, be a reliable source of energy, considering the amount of energy we use. It's often actually, most of the solar power in the world is actually in remote places where they have massive, massive solar cells that just take so much energy. For example, in the Middle East, pollution, although they do use quite a lot of energy to in order to manufacture these solar cells in comparison to just wind being something that to turn. In sunny conditions, it's very reliable. However, that means it's limited to daytime and daytime without clouds. Initial costs are therefore quite high, but therefore it's free beyond that point, and the running costs are basically really small. Okay, so we've done solar, we've done wind, now geothermal. So where does geothermal come from? Geothermal is energy from underground sources. So we already discussed this. So imagine you have like rocks in the ground, and what happens to these rocks, or rocks that lie quite near the surface. And these rocks that lie quite near to the surface are quite hot because of the fact that you have your radioactive elements within them that cause nuclear fusion that release energy. Is this for EdXL? No, unfortunately, this is for AQA. Maybe I should make that a bit more clear. Just AQA, sadly. But yeah. Okay. Good things about geothermal is that it's brilliantly free, it's very reliable, and it barely does any damage to the environment. Geothermal power can be used to generate electricity, to heat buildings. It's got loads of uses, geothermal energy. It's really very useful. But as with anything, there are always drawbacks. So, what are the drawbacks of geothermal energy? Well, the main drawbacks is that there aren't many suitable locations where you can just get these geothermal locations for power plants, and the cost of building a power plant is often so high in comparison to the actual energy it's producing. So the main drawbacks, therefore, are the costs of it and also the locations. It's really hard to get. Okay, so we've looked at those two. Now let's look at the other three. So we've got hydroelectricity. So just think, if you're unsure of hydroelectricity, just remember hydrogen, therefore there's water. So what happens is hydroelectricity all comes from falling water in a dam. So a dam is something that holds lots of water. What happens is the water is falling down, 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 and what it does is it turns these turbines. So you have these like weird cylinder things, and these turbines are then turned, and then since turbines are turned, this has tiny little generators inside of it, and these generators are then turned to produce electricity. And that is how hydroelectric power works. So it gets falling water, it then causes the falling water causes the generators to turn, then causing the electricity to be created. Now, what is the major issue with hydroelectric power? It's really bad for the environment. It's got flooding of valleys. If you looked at, if you did geography, then you'll know how it flooded so much of the Amazon rainforest just because it can get out of control. And because of the floods, it actually kills so many habitats as well because it's taking up a lot of land. So it's really bad, but also because there's big disadvantages, that means there's also a big advantage. And that means that it can provide energy in an immediate response. So when there's suddenly an increased demand for electricity, for example, there was actually a study done where lots of people were watching the show Coronation Street. I don't know if you're familiar with it. You should be if you're British. So lots of people watch Coronation Street at a certain time of the week. Now what happens is, as everyone's watching it, immediately after this show, what do they go and do? They go and create a cup of tea. And this then means that there's actually a really high influx in the amount of energy needed. And this is actually a real problem because what happens is the energy demand is higher than the energy supply because everyone needs energy all at once. Is this at Excel? No, it's not. Sorry. So yeah, there's a high influx of energy, and because there's a high influx of energy, you need a high amount of energy to supply that. And hydroelectricity can solve this problem because all you have to do is let the dam go. All of the energy goes down. It then turns the turbines, which turns the generators. Okay, so that's hydroelectricity. Then moving on to wave power. A lot of people get confused between hydroelectric dams, wave power, and tidal power. Now, in all of them, they all require. Are you going through alpha, beta, gamma? Yes, I am. I'm going through all the content, so I might just skip to that after this because that's what a lot of people struggle with. It's up to you guys. Tell me what you want me to revise, and I can do that as well. I'm flexible. But yeah, so you've got wave power, tidal power. There's not too much of a difference here. So in terms of wave power, you just have loads of turbines that are found in the waves along the coast. So imagine you have a little beach and you have these little wave turbines. Now, waves are caused by the main difference between waves and tides. Waves are caused by wind, and tides are caused by the position of the sun and the moon, which may be really difficult to believe, but that's where tides come from. So when you have a tide, you tend to have like a long river, and then you have this like, kind of bridge. The bridge looks like this, and they all have the turbines in them. And obviously, as the water goes through, this then turns the turbines as it forces it through. And then it's allowed out of this as at controlled speeds. Okay, so tides are produced by this gravitational pull, and wave power is just produced by the wind. So both very similar. You both have turbines, you both are around the water. Wave power is around the coast, and tidal barrages is around estuaries and things like that. Can you make a small summary video of paper 1 in 20 to 30 minutes? You know what? I think that might be a really good idea, and I will try and get that done today for you guys if you find that helpful. Good suggestion. Okay. What are the good things about both of them? They're generally don't create any pollution. The difference is waves are pretty much unreliable, whereas tides are pretty reliable. So that's the main difference in the sense that waves are unreliable because the wind can change generally. However, tides are reliable because they will always happen at least twice a day, and they're quite predictable as well. So that's the main difference. Waves are produced by wind and therefore, unreliable. Tides are produced by the sun and moon's gravitational strength, and that's why they are more reliable. Okay, finally moving on to biofuels and non-renewable and environmental problems. Okay, what are biofuels? You may have learnt about this in biology. These are renewable energy resources. So you either have things like plants or you have, animal remains, animal waste, things like that. And what happens is this is burnt, so combustion reaction happens. And obviously anything that is a combustion reaction releases energy, because remember, this is going into borderline chemistry now, but remember, combustion is an exothermic reaction. It releases energy, and therefore biofuels use this energy that is released to generate electricity. Okay. Okay, and good things and bad things. So biofuels are fairly reliable. Crops take a short time to grow. Different crops can be grown all year round. However, they cannot really respond to immediate demands, because imagine having to get the crops ready to burn the crops. By the time you have their energy, people would have already finished Coronation Street, the second episode. Yeah. So it's just not viable enough. Now, the cost to refine the biofuels is also very high. So you've got the high cost, the high ability for it to not be able to respond to immediate energy demands, so it's not too useful. However, it can be used for things like transport, where it's already in the car, so it can respond immediately because it's in there. Now, let's look at non-renewables. Are non-renewables actually reliable? Things like coal, oil, and gas. Well, in all honesty, yes, they are. Non-renewables are very reliable. You've got all you have to do is burn these fuels and they release a lot of energy. And that's why we've been using them all this time, because they meet the current demand and they can respond to things really quickly. So the reason why we have to change, however, is because A, it's bad for the environment, and B, it's just not good overall. Hi for everyone who's joined. Welcome to the stream. Okay. So what are the environmental issues with non-renewable though? So I'm pretty sure you can assume coal mining. Now, extracting the coal takes up a lot of the landscape, ruins the landscape, and ruins habitats. Oil has lots of spillages. This can cause serious environmental problems, because if oil gets into the water, then a lot of the sea creatures will die. Then you have nuclear power. Now, nuclear power is actually very clean. The only issue you have is once you're done with that nuclear power, you've got to get rid of the waste. The waste is very dangerous, and you can't just throw it in the air. You've got to dig it deep down underground, where there's other nuclear substances like uranium, and there will be safe. So, believe it or not, nuclear fuel is actually really cheap, but it's having to the overall cost of the power, making the nuclear reactors costs a lot of money. And also, nuclear power has lots of bad things because it can cause catastrophes. This is triple science, but obviously it might contain combined science stuff in it. I think so far everything I've discussed is for the combined science specification as well. Okay. Finally, trends in energy use, and then we're done with this first topic. So, Over the 20th century, the electricity use of the UK has hugely increased, as you can imagine. Things with like technology, the population increasing, we're just bound to using more electricity. Now, since the beginning of the 21st century, the electricity use in the UK has been decreasing as we make appliances more efficient. So it might be hard to believe, but so obviously since the 20th century, you have an increase in the use of electricity. However, in the 21st century, you start to get a decrease. Now, you may be asked, why is there this decrease? Well, as I just said, the reason why there's this decrease is because we're creating devices that are more efficient, which means less electricity is needed to perform the same functions. Okay. Okay, so people now have made obviously a conscious effort to try and move towards renewable because we know the devastating impacts. So we need to um, eventually get somewhere. The reason why there's this movement towards the renewable energy resources is mainly because of pressure from other countries. The public has meant that um, the public has made the environments aware and introduced new targets for using renewable resources, which puts pressure on energy providers. There's also, car companies. Car companies have been massively affected by this change in attitudes towards environments. People are less inclined to buy, fossil fueled cars, and they want to buy switching to electric, switching to hybrid. The popularity is increasing. Okay. And finally, just the last bit, the use of renewables is limited by three things. So how is the use of renewable energy limited? So firstly, reliability. We know that they are less reliable because a lot of them are dependent on environmental conditions and things such as wind, solar power, which is not always constant. Therefore, it's much harder for it to, supply to immediate demand. Now, another thing, money. Now, building these renewable plants cost money because currently we have non-renewable plants, which therefore, in order to use energy from them, it's much cheaper. But not for renewable energy, you're going to have to create whole new plants because they function in a whole new way. So some people don't want or can't afford to pay, and there are arguments about whether it's ethical to make them or not. Okay. And finally, the third factor that limits the use of renewable electric energy is politics. Okay, because there's things such as like protesting. Certain areas don't want to have, the ugly wind turbines or the solar power cells in their usage. Um, Making personal changes is also quite expensive. Imagine having to go to electric, it requires a lot of energy and things like that. Okay, so that is the first topic done. I'm so sorry that took a bit longer than expected. So we've gone through energy. So things we still need to go through is electricity, particle model, and atomic structure. So electricity is all about like circuits, particle model of matter is all about particle motion in gases, and atomic structure. So someone did recommend, yeah, this is AQA by the way, someone did recommend making a video which might summarize all of these. I might do that because this is taking a little bit of time. What would you prefer? Please tell me in the chat. So would you prefer me to continue with the live stream, or would you prefer me to make like a shorter video for the rest of the topics? Okay, 1 second. So would you rather me go through the rest of the topics now then, I guess? Okay, that's fine. It's up to you. Um, yeah, okay. I'll just go through the rest of the topics then, if you prefer that. Okay. Well done, by the way, guys. You've made it all the way this far. I'm very proud of you. You can tell me how GCSEs are going. Feel free to. How was English Literature Paper 2 today? I hope it went well. Okay. So I'm going to go over electricity, particle model of matter, and atomic structure. Is there any order you want me to do those three? I can put it here. So we've got. Okay, so unseen AQA was good. Poetry was easy. It was all right. It was so good. Power and conflict was easy. Okay, so it seems poetry's went good. That's great. Ozymandias. Also, some of you do power and conflict, some of you do love and relationships. Is it true that in love and relationships, which one came up? I think it was because I'm hearing other people say things. I can't remember what it was, but because I'm just getting my information because obviously I'm not doing GCSEs, so I'm just getting my information based on students of what they're saying the questions were. So was unseen poetry really good? That's great because normally unseen poetry is where everyone just fails. Okay, electricity, please. I'm an IGCSE student. Can I watch this live? Honestly, I'm gonna be thing. I do not know too much about IGCSE content. I don't know if you're able to watch this if the content is the same. Um, okay. When we two parted, before you were mine, before you were mine, before you were mine. Oh, okay, before you were mine. So, did you like before you were mine? Um, seems like an interesting poem. I mean, you guys kind of knew which one of the poems it could be because it's obviously not the ones from the last couple of years. And Inspector Calls was kind of questionable. Oh, okay. What was Anne Inspector Calls' question? I think was one of the Anne Inspector Calls about. I think one was about the inspector, right? I'm not sure. What do I do to get a grade 5 in physics if I do combined foundation? Okay. So in order to get a grade 5, I would say the best thing is in terms of physics, the best resources are physics and maths tutor. Physics and maths tutor has some really good notes that you could use to revise. And I think in terms of physics, it's mainly the concept. So electricity is the bit where most students fail on. So spend a long time revising circuits, series circuits, parallel circuits. Um, in terms of practice questions, of the physics exam is calculations. So you should really try and do lots of calculations questions. That would be helpful. Um, easy, but had to rush the last question on the 8 marker. Oh yeah, because you guys had, was it 2 hours, 15 minutes to do the exam? Sorry if I'm going off topic for everyone. Scaffolding. Scaffolding. Oh, was that the unseen poem? Oh, that's cool. Um, how women were. Oh, is that the question for Anne Inspector Calls? How women were shown? Should I watch free science lessons? Yeah, free science lessons is really good for physics. One. Just can you hear me now? Sorry about this. It's constantly just like I think loads of people are using the national grid. Okay. Is this working? Can you hear me well or no? I guess if you can't hear me, then it wouldn't be on there. Okay, sorry. So I'm getting off topic now. I should probably just continue with physics, but yeah, I should. Okay, let me go back to physics. I'm getting off topic. I'm glad your exams went well. So we're going to go into electricity now. Okay. So electricity, all about circuits. So this is most students' weak point. Most students lose marks on this. So let's go through this in lots of detail. So firstly, you need to know definitions. What does current mean? What does potential difference mean? What does charge mean? So let me write them in brackets here. Current. What does potential difference, also known as voltage, mean? What does charge mean? Feel free to put your answers in the comments. So these are the couple of things that you need to know. One second. Yeah, I'm going to do the national grid in characters like that as well. Would a 6 marker be on a practical for gamma, beta, alpha? It's possible that it would be. Yeah, it's possible that would be. In terms of predictions, I'm not too sure. I feel like there's going to be some stuff on radiation, but I'm not too sure about anything else really. I feel like make sure you do radiation and make sure you do electricity. Okay, but just back to this so that we can get the content done first. Sorry. So, current. What is current? So, current is the flow of electric charge. So, it's the rate of the flow of electric charge around a circuit. Rate of flow of electric charge around a circuit. Yeah, perfect. Rate of flow of electric charge around a circuit. So that's for that is current. Now, voltage. What is voltage? So, voltage or potential difference is basically the thing that pushes charge around a circuit, pushes the charge around a circuit. So, in terms of the definition, potential difference is the difference in energy over a component per coulomb of charge. So, the difference in energy over a component per coulomb of charge. Now, coulomb is just how charge is measured. Okay. So, just looking at this, rate of flow of electrons. So, that's just how quickly basically electrons are flowing around a circuit. That's what current is. In terms of voltage, voltage is the difference in energy. So, when you're looking at a component, right? So, imagine you're looking at a bulb and you wanted to find the voltage of a bulb. You would therefore connect the voltage in parallel to the bulb, and you can see in the definition it says the difference in energy over a component, and therefore that's why it's the reason it's called the difference, because it's basically this energy take away this energy. That is practically what voltage is. What is a circuit? How would we define it? You wouldn't really be asked what a circuit is. I feel like it would just be where electric current can flow. Okay, so where electric current can flow, and it can power things. Okay, so we've done current, we've done voltage. Charge. What is charge? So charge is just something that can either be like positive or negative, and it just moves around a circuit. So everything is based around charge. You see, current is the rate of flow of electric charge around a circuit, or electric. Yeah, the rate of flow of electric charge around a circuit or electrons around a circuit. Voltage is the difference in energy per coulomb of charge. Charge is just something that moves around a circuit, positive or negative. Now, there's a couple of equations you're going to need to know, but obviously, actually, you don't need to know it because you're given the equations. But the first one is just Q equals IT, charge is equal to current times time. Things you do need to know are the circuit symbols. So, for a cell, the cell looks like this. So remember this cell looks like this, sorry. The smaller line is on the right-hand side. And you've got positive to negative. So positive terminals on the left. You don't always have to write the negative, but positive's good. So that's what a cell looks like. Now a battery is just when you have two cells connected together. So you've got one like this, one like this, one like that, one like that. And that's what a battery looks like. And you just put the positive end there. So that's a cell, that's a battery. In order to do a switch, so a switch is just something that's open, that's an open switch, and a closed switch just looks like that. A bulb, we've already looked at what a bulb is like. You just have this cross. And then you have a fuse. So a fuse looks like this. You don't tend to be asked about a fuse. It's just needed for the other topic about safety. An LED, so a light emitting diode, looks like this. Remember to draw the arrows because a way to remember where the energy comes from is you're just pointing to the direction of where it's coming from. Don't we apply that second law? No, we don't need to apply that. That's not GCSE spec. You don't need to know that. What is a fuse? What does it do? Okay, so a fuse is basically something that when there's... Okay, let me just do this on a separate page. So what happens is, right, when there's too much electric charge, basically when you're at risk of being electrocuted. So when there's too much electric charge flowing through a circuit, so too much current, the current is too high, then what happens is this, and what it does is it melts. It melts, and therefore, as it melts, it prevents any current from continuing to flow. And because it melts, it therefore saves you because then you don't get electrocuted because the current is getting so much, it could start traveling through you if you're touching the wire. So the fuse basically acts as a safety mechanism. I'll go through that in a bit more detail, but I hope that's all. We don't need to know the second law or thing. It's not in the GCSE content. Yeah, that's definitely not in the GCSE content, don't worry. Yeah, okay. Okay, other circuit symbols. So there's also thermistor and resistor. So all the different types of resistors. So a normal resistor just looks like this. That's what a normal resistor looks like. A variable resistor has an arrow going through it, like that. A thermistor has this weird line going through it. So it goes straight and then it goes like diagonal. And you've also got a light dependent resistor. So you have this circle, you have the resistor shape, but instead of it being emitted, it's obviously dependent. So it requires it. Okay, so it's definitely not in the specification, that law. Don't worry, guys. It's definitely not in the specification. Okay. Anyway. Oh, and then you should obviously know voltmeter is just V in the middle, ammeter is just A in the middle. A voltmeter measures the voltage, a ammeter measures the current. Okay, so they are the different things. We'll look more in detail. Repeat, please. Or what did you want me to repeat? I can repeat anything. Just tell me which ones you want to read. Oh, the different circuit symbols. I can just go over them. Okay, so you've got the cell here. So that's a cell. A battery is two cells connected together. So it's obviously double a cell. You've got a switch and that's open, that's closed. You've got a fuse, not a fuse, a bulb here, a filament lamp. So just to make it easy for you to remember, this filament lamp is basically one of those bulbs that looks like this with those filament wires in it. So that's what that bulb looks like. You've got a fuse, you've got a light emitting diode here, and you've got a light dependent resistor here. You've got a resistor here, a normal resistor, a variable resistor here, a thermistor here, and a voltmeter and ammeter. So voltmeter measures the voltage, ammeter measures the current. Okay. The middle three diagrams. Astrophysics. Astrophysics is paper 2. So I'm just going over paper 1 topics. Are we getting all the physics formulas? Yes, you are. You are getting all the physics formulas. The thing that they want you to do in the exam, though, is rearrange the formula so that it makes more like, for example, specific heat capacity. They'll give it to you like this. Oh, what is going on? 1 second. So for specific heat capacity, 1 second, everything is going a bit mad. So for specific heat capacity, it'll give you energy transferred is equal to mass times change in temperature times specific heat capacity, and then they'll require you to like rearrange it in order to put it in terms of specific heat capacity so you can work it out. 1 second, the screen has just disappeared. Okay. Okay, so we've looked at the different components, we've looked at current, we've looked at the definitions, we've looked at the diagrams. The next thing we need to look at is resistance and what are ohmic resistors, and the next required practical. Can you tell us the topics included in paper 1 in GCSE Edexcel? I actually don't know what's included in Edexcel. I just am familiar with AQA. Unfortunately, I'm so sorry. You can, if you get the spec up, then yeah, I'll deal with that in a second. Let me just finish trying to go through the content, okay? So the next thing is required practical. So you've got the first required practical, but that's based on resistance. So let's first look at resistance before we look at the required practical. So resistance, what is the definition of resistance? Resistance is basically how difficult it is for charge to flow. Well, the main factor of resistance is what we call temperature. Okay. So the main factor that affects resistance is temperature. So I'm going to explain to you how temperature affects resistance. So what we do is imagine there's a wire, okay? And the wire contains the normal atoms, because obviously it's made of material. So a wire contains normal atoms. Now what happens is you have current, and current travels in a circuit. So imagine current is represented by this yellow. So current is trying to travel through the atoms. Now what happens is, as the current is trying to travel through, because if there's a temperature increase, as we know, when there's a temperature increase, the particles have a higher thermal energy and therefore have a higher kinetic energy. Now, what happens when they have a higher kinetic energy? This means they move about more, right? So as the particles move about more, this then means it's more difficult for the current to flow. Because imagine, is it easier to walk through a corridor where there's loads of people, or is it easier to walk through a corridor where there's no one? It would obviously be easier, it would take less energy to walk through a corridor with less people. And therefore, it's much easier to just go through. Is this grade 10? I don't know the American system. But yeah. This is just for like the British system. Okay, so that's what resistance is. That's where resistance comes from. And therefore, from the idea of resistance, you need to know the idea of what an ohmic conductor is. So an ohmic conductor is something, a component within a circuit that follows Ohm's law. And you now may be like, what is Ohm's law? Okay. Okay, sorry. So Ohm's law is basically how resistance is constant. So V equals IR. Basically saying how voltage is directly proportional to current, and if you were to rearrange it, because V equals IR, so resistance is equal to voltage over current, and therefore it's inversely proportional to them. Therefore, if we had a graph and we have current and voltage, it should produce a graph like that. Basically saying that it's constant. So an ohmic could be something which has a constant resistance. Yeah, perfect. Voltage is directly proportional to the current at a constant temperature. So as long as it's a constant temperature, it works. Okay. Now, for some components, the current through the wire is changed. So as you change the current, therefore the resistance will change, and therefore the voltage will change. Now, okay, let's just, before we go too much into ohmic conductors, let's just make sure you know how voltage and current differ in series and parallel circuits. Okay, because we haven't gone too much over that. So we've got a series circuit and a parallel circuit. So current and voltage. So a series circuit doesn't have any branches. That's the main difference. Okay, there's no branches found in a series circuit. So let me show you an example. So you've got the battery or the cell here, ammeter here, ammeter here. So a key thing to remember is in a series circuit, the current is the same everywhere. Okay. So the same, each of the components have the same content. Again, okay, so forces is not discussed in paper 2, by the way. Paper 1, so you don't need to worry about forces. In terms of the topics for paper 1, it's just energy, electricity, particle model of matter, and atomic structure. So those 4. Okay. So in series, the current is the same at every single component. Okay. And the size of the current is therefore determined by the total potential difference of the cells. So if the potential difference here is 4 volts, then the current will then be determined, and say the current is 2 amps. The current 2 amps will be here, it'll be the same here, it'll be the same here, it'll be the same here. Because remember, current is the same anywhere in a series circuit. But what about voltage? How is voltage in a series circuit? So let's draw another circuit. The same one, but in order to measure the voltage, we'll obviously need voltmeters. So let's put a voltmeter across this component and voltmeter across this component. So in a series circuit, the total potential difference of the supply is shared between the various components. So say if this was 9 volts, then the voltage to the first bulb is going to be 4.5 volts, and the voltage to the second is going to be 4.5 volts. So it's shared equally. From your knowledge, is it okay to tell me the topics that are going to come up? Well, obviously, it's going to be really difficult to predict the topics that are going to come up in a paper, because you're supposed to revise everything so that you are prepared for everything. So it's not like, I think most of them will come up. Most of the topics will come up because unlike biology, physics doesn't have too much content. So they tend to just ask you loads of calculations. Okay, so we've talked about voltage in a series being shared between the components equally, and current in a series being exactly the same everywhere. In terms of parallel, so we're looking at parallel circuits, each component is separately connected to the positive terminal and the negative terminal. So in series, each of the components are connected end to end between the positive and terminal. So each of the components are connected end to end from here to there. Whereas in a parallel circuit, they all have their own individual connections. So you've got ammeter here, and you've got a component in the first branch, imagine, and say you've got your ammeter here. Don't get overwhelmed by the amount of ammeters. The reason why is just so we can show that we're measuring the current. And if you want to measure the voltage, you just put it above in parallel to the component. And then you've got another bulb, ammeter, voltage of this component. So in parallel circuits, every single component gets the full source of potential difference. So the potential difference is the same across each component. Therefore, if it's identical components, it will have the same amount of voltage. So therefore, if you've got a 9 volt, then the voltage going through the first bulb will be 9 volts, and the voltage going through this one will be 9 volts. It's the same, and if they're the identical components, they will have the same ones. Okay. I'm sorry for this abrupt ending, but unfortunately I have to go. It's a bit of an emergency. I'm sorry. I hope you found this live stream helpful. It was a little bit lengthy. I went through energy and a little bit of electricity. If you do have any questions, just do it on the latest community tab. I might be able to see it then. But thank you for all tuning in. I'm sorry I've had to cut it short a little bit. I'll try to put some more up on Instagram to help you guys out. See you soon, and all the best for your exams tomorrow.